Okay guys, in this video we're going to be talking about the first law of thermodynamics. I'll also talk a little bit about state functions and path functions. We'll begin right there. State functions are properties of our system. For example, all of our variables such as the pressure, volume, number of moles, and temperature, these are all examples of state functions. Later in this video we'll talk about internal energy as well, and in a forthcoming video we'll talk about enthalpy. State functions depend only upon the present state of our system of interest. It doesn't depend on how the system got into that state. Essentially, the variables define the state. So whatever state you have, that state has a certain number of variables. Also important about state functions is that a change in the state functions, such as a change in the pressure of the system, depends only on the final state and the initial state, and you typically calculate that using a final value minus initial value to calculate that change. Path functions, on the other hand, these are quantities that depend upon the path between states. In fact, they only emerge when the system is changing from one state to another. The only two path functions are work and heat. Work is represented by lowercase w, and as we've seen before, heat, at least in these lecture notes, is being represented by a lowercase q. It would be improper to use the delta w or delta q notation. This doesn't make sense because work and heat are not state functions. Likewise, you wouldn't put a subscript on work or a subscript on q, because that would imply that the system in state 1 has a value of work or a value of heat, which is not true. To give you an analogy about the difference between state functions and path functions, we have this picture here. You can think of the potential energy of an object as being a state function. Whatever height you are above the Earth's surface determines your potential energy. So at base camp here at the bottom of the mountain, one has a certain potential energy, and if you go to the top of the mountain, you would increase your potential energy. The difference in potential energy only depends upon the difference in height, and it doesn't matter what path you take to get up the mountain, the change in the potential energy is always the same. However, the work in getting from the bottom of the mountain to the top of the mountain does depend upon the path. So going up, just going straight up the mountain, that involves one amount of work, versus if you take some long drawn out path, say going around the mountain about 5 times to get up to the top, that would involve a different amount of work. So we have a difference between state functions, which are properties of the system, and path functions, which only come about when the system undergoes a change in state. Let's talk about the internal energy now. So internal energy, U, is the sum of the kinetic and potential energies of all of the particles within your sample. U is an example of a thermodynamic state function. It's also extensive, which means if you double the size of your system, the energy of your system will double. And it's measured in units of joules and kilojoules. And here I have an equation showing you how the internal energy fits in with the total energy of your system. So here the total energy of your system would be a sum of the system's overall kinetic energy. So for example, if the system is moving through space with some speed, it would have an overall kinetic energy. Chemists do not care about this kinetic energy. Likewise, if your system is in some gravitational potential field, for example, the difference between doing your chemistry experiment on the first floor of a building versus the fourth floor of the building, technically speaking, on the fourth floor of the building, the system would have a higher potential energy. However, chemists do not care about that particular potential energy. We only care about the kinetic and potential energies involving the particles themselves. That is the internal energy U. Okay, so this is the quantity that is of interest thermodynamically speaking, and technically if you would like to calculate the change in the internal energy, you could imagine at least taking the final energy of your system minus the initial energy of your system for whatever process you're considering, a chemical reaction, for example. However, you should note that this equation is never really used in practice, at least for internal energy, because there's no way to directly measure the absolute energy of the system. You can measure energy changes, but you can't measure absolute energies. One more comment here. The internal energy of a system can be changed when it absorbs energy, which we would call a positive change in the energy, or it can release energy or evolve energy, which would be a negative change in delta U. So if delta U is negative, the system loses energy. If delta U is positive, the system gains energy. There are two known ways in which a system can gain or lose energy, and that is through the processes of work and heat, which we'll talk about next. We've already talked a little bit about heat, actually quite a lot of bit about heat in the last couple videos. Here I'm just reminding you that heat is a type of energy transfer associated with a temperature difference between our system and its surroundings. Now we know that we're supposed to call heat a path function. It's measured in units of energy, joules or kilojoules. And then we have the following sign conventions. Okay. When heat is positive, that means you are adding energy to the system. So the surroundings is at a higher temperature than the system. Energy, thermal energy, will flow into the system, increasing its energy. We call that an endothermic process. Contrast that when Q is negative. So when you have negative heat, that means thermal energy leaves the system. Typically the system would be at a higher temperature than the surroundings. We call that an exothermic process. So this is an important sign convention that you need to be aware of. And you definitely need to know these terms, endothermic and exothermic, and what they mean in terms of the heat. So this concept, these are used throughout general chemistry and beyond to explain all sorts of observations. Okay, so these are fundamental definitions that we need to know. We'll be talking about heat flow during chemical reactions, so we'll be talking about the heat of a chemical reaction. Typically, the chemical reaction will be carried out at a fixed temperature and fixed conditions. Most commonly, pressure is a fixed value. However, you can also have a constant volume process. For example, the bomb calorimetry experiments we described in one of the previous videos are carried out at constant volume, although the solution calorimetry experiments that we talked about, those are carried out at constant pressure because the reaction is open to the atmosphere. Here I'm just showing you two reactions. This reaction here involving the barium hydroxide hydrate reacting with ammonium nitrate. This is an example of an endothermic reaction, one that absorbs thermal energy from its surroundings. Here, this combustion reaction of methane is exothermic. It produces energy. Here we have a little problem where we are being asked to comment on the thermodynamics of this reaction. So we have ammonia is burning in the presence of a platinum catalyst to produce nitrogen monoxide and water. If 4 moles of ammonia is burned and 1,170 kilojoules evolves as heat, they want us to comment, is the reaction endothermic or exothermic, and then what is the value of the heat? Well, the word evolves tells us that this reaction releases energy. So this would be an example of an exothermic reaction. And for an exothermic reaction, the value of Q is negative. So the value of Q would be minus 1,170 kilojoules for every 4 moles of ammonia that's burned. Here, in the next slide, we're going to talk about work. So work, like heat, is a path function. It's a type of energy transfer. However, work is associated with the difference in force between the system and surroundings. And typically there will be some movable wall between your system and surroundings. It may be a real wall or an imaginary wall, but anyway, something moves in the system or the surroundings, and work is done. We have the same units. Work is measured in joules and kilojoules, and we have the same sign conventions. When work is greater than 0, that means that the surrounding does work on the system and causes the system's energy to increase. However, when work is negative, that means that the system does work on the surroundings, and that causes the energy of the system to decrease. For chemical reactions, the most common form of work that we encounter is so-called PV work, where you have a gaseous reaction that involves either an expansion or compression of the system. And when the system expands, when the volume of the system gets bigger, we say that the system is pushing against the surroundings. That is, the system is doing work on the surroundings. Contrast that when you have a compression, the volume of the system decreases. That's due to the surroundings doing work on the system. The way you calculate PV work, at least for a expansion and compression where the external pressure is constant, so if the external pressure is constant, then you calculate work using this formula here, minus the external pressure times the change in volume. Very often the pressure is measured in units of atmospheres, and the volume is measured in units of liters. You can convert liter atmospheres to energy or to joules using this conversion factor here. I think we have a couple of problems upcoming that deal with this equation. We'll get to those in a second. First, we're going to talk about the first law of thermodynamics. It deals with the total internal energy, and by total internal energy, I mean that includes both the system and the surroundings. And so the law is that the total energy of the system and surroundings is a constant, which means that energy can neither be created nor destroyed. The first law of thermodynamics is also called the law of conservation of energy. So here in the equation, delta U total, this includes both the change in the system's internal energy plus the change in the surroundings' internal energy. And the sum of those two changes must add up to 0 for any process. I'll just make a comment about the notation. You'll see that I've included explicit subscripts for the change in the internal energy of the surroundings and the change in the internal energy of the total system. However, for the system, I didn't use subscripts. I put those in parentheses. The notational convention is that when you don't use a subscript, you're automatically referring to the system. However, if you're referring to the surroundings or the total composite system, you need to put in the subscripts. In any case, given this relationship between the change in the internal energy of the system and that of the surroundings, you see that any change in energy of the system is equal and opposite to that change in the surroundings, and vice versa. There are two ways in which the internal energy of the system can change. Either heat can occur or work can occur. So this is an alternate or a secondary statement to the first law of thermodynamics, and we're going to work this. We're going to use this equation in a couple of example problems. So, in this problem, we're considering the combustion of methane. Okay, and so we're told that at 1 atmosphere, the heat of this reaction is minus 855.5 kilojoules. So they are telling us that in this case, Q equals minus 855.5 kilojoules. And then they tell us some information about the volume change that occurs during this reaction at a pressure of 1 atmosphere. So they want us to calculate the work. So for PV work, That's the type of work that's happening in this problem. Work equals minus the external pressure times delta V. The external pressure is 1 atmosphere. And then the change in volume is going to be, the final volume is 28.7 minus the initial volume of 86.2. And we're going to convert that liter atmospheres to joules. So we're going to use 101.325 joules per liter atmosphere. So we'll calculate the volume change, 28.7 minus 86.2. It's negative. That means that the system is being compressed, so the surroundings is doing work on the system. We'll take that times the minus sign out front, times our conversion factor, and I'm getting plus 5.83 kilojoules. So I went ahead and did a joules to kilojoules conversion right there. To get the change in the energy, internal energy of the system, we want to add the heat and the work together. Okay, so I'm going to take that 855.5, which is negative, and I'm going to add to that plus 5.83, and we get minus 849.7 kilojoules. So overall, the system loses energy, and it loses most of the energy through this heat, even though it gains back a little bit of energy through the work that's being done on it by the surroundings. So this is an example of a first law calculation. I believe we have a second example. This one's a little bit more physicsy, if you like. So we've got a gas that's enclosed in a system. It's basically a piston, okay, and it has some mass on top of it. And once you add the mass, what happens is the piston, the volume decreases. So we're doing work on the gas that's inside this piston. They want us to calculate the work that's done, and they say that the heat, as the compression occurs, they say that the system evolves 1.5 joules of heat. So we know that the heat is minus 1.50 joules. They want us to calculate the work. And so here, this is where the physicsy part comes in. So work is minus the external pressure times the volume change. Pressure, the external pressure, is due to the mass. Okay, and so there's a mass, there's a force of gravity pulling down on the mass. We're going to write the external pressure as a force divided by a unit area. So the piston has a surface area, and then the mass exerts a force on that area. And that's what pressure is. It's force per area. Volume, the volume change in this case, since the area of the piston doesn't change, only the height changes, we can write this delta V as the area times the change in height. The areas cancel out. We can write the force as a mass times the acceleration due to the gravity, delta H. Let me check my sign convention real quick. When delta H is positive, we get a negative work. That's correct. When delta H is negative, we would get a positive work. So that's, we've got our sign convention is satisfied. So this is the equation that we want to use. We're going to plug in the mass, 2.20 kilograms, acceleration due to gravity, 9.81 meters, and I got the units wrong. It should be per second squared, not meters per second, right here. So that's a typo. It should be to the minus 2 power. And then times the delta V, let's see, it says the mass is lowered by 0.25 meters, so that delta H would be a negative 0.250 meters. So we'll go ahead and run these numbers here. These are all in SI units, so we're going to get 5.40 plus 5.40, and that's kilograms meters squared per second squared, which is equivalent to the joule. So to get the delta U, we add together the heat and the work. In this case, it's going to be minus 1.5 plus 5.4. And we get a overall plus 3.90 joules. So in this problem, the delta U is positive. Overall, the system gained energy when it was compressed, even though it lost a little bit of energy through heat. Okay, so that's another first law type of problem. Well, the next topic, enthalpy, we are going to save for the next video.